This is Todd McClanahan with Autoform, and in this video, I'd like to talk to you about part and tool compensation, methodologies that you can use to improve your body in white assembly accuracy. Autoform has long offered solutions to allow users to study the effects of sheet metal forming on single parts, but now with our new assembly solution, we can begin to understand what happens when these parts come together. What does that mean? It means that we now have different groups and different disciplines that have to work better together in order to achieve the project goals. If we look at the integrated process chain, blue tasks typically completed by the forming side, and the gray tasks, those typically completed by the body and white side, we see these things happen concurrently. In a large organization, we also tend to see the silo effect, where groups don't always work well outside their own boundaries and information is not always shared or communicated. So prerequisites for us to have success with these methodologies I discuss are that we have to, one, look at a product focus, looking beyond just the single parts, but understanding what happens when they come together. Also, we have to improve our communication and collaboration in order for us to have success, not only with groups at our own companies, but also when working with other companies. So let's look at the 7 steps that we need to take in order to achieve improved body and weight accuracy using part and tool compensation. The first step that we need to complete to move forward to improve body and weight accuracy is that we need to have complete, robust forming simulations. So with Autoform forming, we can of course set up our forming process, make sure that it's feasible. We can create quality tool geometries. We can make sure that we have reasonable press conditions with good forming. We can make sure that we have optimal material utilization and we're achieving the expected accuracy within a given tolerance. That's great, but it gives us a single forming simulation result. What's more important to understand is, can it handle variation in production? So can we go through, make sure that we can handle different press conditions? Can we handle a new coil of material with different properties? And can we understand and accept the lubrication and friction changes? Can that be handled by our process as well? That's really the biggest step to get started, is make sure we have nice, robust forming simulations. The second step, after completing robust forming simulations, is to set up our initial assembly using forming results for each of the parts. We can set that process up with the number of processes we think we need to bring these parts together. And once doing that, we can understand, number one, is the process feasible? Do we have clamping and joining forces that fit within an acceptable range? Are our gaps between parts acceptable as well, or is it too far or too big of a gap? And most importantly, understand if the accuracy that we get is acceptable. If so, we can move forward. If not, we now have to make a plan and move into step 3. If we have not achieved the accuracy that we need for our assembly, we need to move into the next process, which is compensating the selected parts. Now, for us, we can decide which part has the most influence in the assembly, and we can determine that in our early feasibility studies. We can then spin off a new simulation, selecting those target parts for compensation. What that allows us to do is build that into our assembly process, leaving all other parts as they were, but compensating a single part to a new geometry that, when combined using the same process, ultimately leaves us a result that is very accurate and meets our tolerance expectation. That now becomes the target geometry for that single part that should be used in combination with the other parts. Once we've compensated a single part and seen that we've achieved the accuracy, we still need to complete the next step, which is validating the compensated assembly simulation result. So we can see, of course, that we've achieved the accuracy that we want for the assembly, but it's more than just the accuracy. We can also begin to study the predicted splits, make sure that the clamping and joining forces are in acceptable range, and make sure that there's not any large gaps between parts. Also, we can look at the forces at each of the joins and make sure that they don't get too high as we go through the assembly process. We can understand the hemming forces required for the tools, and also we can check the surface quality once this part in this particular has been hemmed and see if there might be any surface defect risks that can be created. Once we've done this, we can move on to the next step. Now that we've validated our assembly simulation result with the compensated part, we've only compensated the part. The next step for us is to compensate the forming simulation tooling so that we can actually have tool geometries to make the part that we have to make. So with that, we've gotten a target geometry from assembly. We can now take that back into forming, set that as the reference geometry for the measurement operation, and generate a vector field that allows us to then compensate the tools to create the part that is necessary. So when compared to the target geometry, we actually get a match of the part with the stresses and strains from an actual forming simulation. That's a critical step for us to move forward. So now we have forming simulation tools that create the part that we need. We need to take that as a next step, step 6, back into the final assembly and validate the results. So basically what we need to do is it's a back and forth between forming and assembly. And now that we have tooling that makes the part as determined by the compensation, we now need to take that back in and validate that in our assembly solution one more time. So after all of this effort, we have one final step, and that is to complete and manufacture tooling. So our next step we have to complete is making CAD tooling geometry for machining purposes. We understand that this is now a transition for us. Everything we've done thus far has happened in the virtual world by simulation, but we're now about to cross over into the physical world where things can get very expensive. That's why we've put all this work into and completed all these 6 steps prior to this point. So now we need to make good CAD geometry with this milling data release that can be used for manufacturing purposes. So it's important that you understand we have solutions that can be utilized, the vector fields taken from what we've done thus far, to create a CAD quality geometry for machining of the tools to get you the final results that you're looking for. I hope you enjoyed this video on the 7 steps needed to achieve body and weight accuracy through part and tool compensation. To learn more or talk to your local AutoForm representative, please find us at www.autoform.com. Or to learn more about webinars we provide on this and many other topics, please find us at www.formingworld.com/webinars. Thanks for your time.